Welcome everyone to our new One Word ABC talk. It's my pleasure today to have here Yuexi Wang with us. She's a fifth-year PhD student she will present a joint work with Veronika Rokova, and she's a PhD, so Yuexi is a PhD student at the University of Chicago, and today she will talk about adversarial Bayesian simulation. Thanks a lot. The stage is yours.
Okay, thank you. Hello everyone. Thank you for attending this Thanksgiving special edition of One Word ABC. Today, actually, I'm going to talk about two approaches we have proposed about like simulation-based inference methods using adversarial learning techniques, and both are joint work with my advisor, Veronika Rokova. So given the special background of our audience today, I will just fast forward on the background to make sure everyone is on the same page. So since we're all Bayesian, the basic ingredients here is we assume we observe data set realized from this parametric model indexed by what we call the true parameter theta null. We assume there's a prior distribution over the parameters. We wanted to obtain draws from the posterior that is characterized as the product of the joint likelihood and the prior. So for simulation-based inference, we specifically focusing on situations where the joint likelihood can be too costly to evaluate or just simply intractable, but it can be simply easily sampled from. So some of the classical examples including Hesston model, where people use to like model the stochastic volatility dynamics in finance, and the Lotka-Volterra model, which I will revisit multiple times throughout the talk today. This is another model where people trying to study the interaction between the predator and the prey population in ecology. And something similar to the Lotka-Volterra model is the SR model, where people trying to study how the disease is spreading in the population in the epidemiology. So still give everyone a more concrete idea of what a simulation-based model may look like. I will focus on this Lotka-Volterra model, which is characterized with 4 parameters, theta 1 to theta 4. So basically, the dynamics of the two population is deterministically prescribed by these ordinary differential equations. But to simulate the integer value of the population at discrete time points, we usually use this stochastic Markov-John process to simulate. So imagine we start the two population at the initial values of x0 and y0. So we wanted to simulate the population of the two groups at the next time points. There are usually like 4 actions. It's either the predator or the prey population growing or shrinking with probabilities that is proportional to this one of the 4 terms here. So there's no algorithm to simulate exactly the population at the discrete time points once the parameters are given, but the likelihood for this model is simply unavailable. So that makes it like one of the like benchmark data sets that has been used over and over again in simulation-based inference literature. Since this is the One Word ABC seminar, but I still need to go review the ABC idea a little bit. So ABC has become one of the driving forces in simulation-based inference. The intuition is very simple. We can always simulate pairs of parameters and the synthetic data sets from the joint distribution. Usually we simulate a bunch of parameters from the prior. For each parameter, we pass it through the data generative process, P theta n, and we get a synthetic data set. And we believe that if the distribution of the synthetic data set looks similar to the observed data set, that means the proposed parameter should also be close to the true parameter. So a lot of the literature were focusing on how should we rigorously quantify this similarity. And the starting point of ABC is like we use the distance between the summary statistics on the synthetic data set and the observed data set. So if the distance between the two summary statistics is below this pre-specified threshold epsilon, then we will pick the corresponding parameter and accept it into the posterior. So of course, there are some disadvantage of this method. So the first one, the performance of the such ABC posterior usually rely heavily on the choice of the summary statistics. And when we change the choice of this pre-specified threshold, the posterior shape will vary. And in addition to this accept-reject strategy, people also use other types of kernels, like Gaussian kernels, to weigh the ABC draws. That will also change the posterior shapes. But there are also, but ABC methods enjoy some computational advantages, especially comparing to MC methods that are usually executed in a sequential fashion. The first thing is, especially for this accept-reject strategy, we can draw the candidate parameters independently from the prior. So that makes parallel computation immediately feasible. And also because of this independent sampling of the parameters, the performance of ABC is usually not very sensitive to initialization. So for our two papers, we handle the task of defining similarity to machine learning classifiers. So our intuition is that a good flexible classifier can tell us how similar the two data sets are. So since I already mentioned, we are going to talk about like two papers. So they have a little bit different emphasis. The first one, we're focusing on situations of IID data set. So for example, still the Lotka-Volterra model, we may assume each observation is a time series of the predator and prey population. And we observe, say, like 20 independent copies of this time series. So given the independence assumption, now the joint likelihood have this product form. And the paper is Approximate Bayesian computation via classification. It has been recently accepted by JMLR. And for the second paper, we kind of extension of our first approach. So the second paper, second approach, we propose a Bayesian GANs sampler that can handle dependent data sets. So we can handle, for the Lotka-Volterra model, again, we can handle the cases where we only observe one time series. And because of the inherent dependent structure in the data set, now there's no product form for the joint likelihood. And this paper is now available on arXiv. So now let me start introducing our first method, ABC via classification. So here we use what people usually refer as the classification trick. So the setup here is since we assume we observe like an IID copy of the observed data set, which we refer as the real data set here, we can always simulate M fake observation once we sample the parameter from the prior. And we refer it as the fake data set temporarily. So we can always reframe this task of defining similarity as a classification problem. So basically, we label 1 for the real data set, and we label 0 for the fake data set. So the idea here is if the proposed parameter is very close to the true parameter, then the proposed model should have also similar distribution to the true model. Then we will expect it's going to be a hard task for the classifier to distinguish the two data sets. Then the predicted probabilities on here is the fake data set should be close to 0.5 which is usually the decision boundary. And when the proposed parameter is far from the truth, then the two data sets will be very different in distributions, and the predicted probabilities on the fake observations should be close to 0. And here, if the discriminator class is flexible enough, like contains all the possible functions in the world, the oracle solution to this maximum binary cross entropy loss problem in equation 1 can be written using the density function of the true model and the density function of the proposed model, and then we can rewrite the log density ratio using we can rewrite the density ratio using this oracle discriminator. And since we do not have all the information we want in the world, we just simply replace this oracle discriminator with a discriminator that is maybe trained from a flexible machine learning class. So using this trained discriminator, we can construct either a KL estimator or a likelihood ratio estimator. So we actually consider two versions of the ABC method here. So for the first one, we basically still use the accept reject strategy, but we use this KL estimator as our data discrepancy used inside ABC. And for the second method, this is motivated by the connection between the likelihood ratio and the KL divergence. So we basically use this K hat as a plugin estimator for the likelihood ratio, and that inspired us to propose exponentially weighted kernel for the second version of ABC. So now I will introduce the first version, still the traditional accept reject ABC. So the first two steps are just a very routine. We simulate for each ABC draw, we simulate the parameter from the prior. We generate a synthetic data set that has m IID observation from the corresponding model. But here, for each ABC draw, we need to train a new classifier trying to distinguish the observed data set and this synthetic data set. And we use the returned classifier to construct this KL divergence estimator. And we will pick this parameter only if the estimated K hat is below this pre-specified threshold. So that leads us to the mathematical formulation of the approximation posterior here, which each ABC draw is weighted by this uniform kernel. So we also provide theoretical results in our paper. We show that the posterior contraction rate of this AL posterior depends on two terms. The first one is the estimation error, which is the difference between K hat and the empirical KL divergence. And we referred it as delta n. And the second term is the decision threshold epsilon n here. So with this theoretical results, the consistency of this approximation is guaranteed as long as we have a vanishing threshold. But still, for this method, it still requires us to specify this threshold epsilon n, and the proper choice of epsilon n can also still be unclear for complex models. That's why we introduced the second version of ABC kernel here. So as I mentioned before, this is motivated by the connection between KL divergence and the likelihood ratio. We propose another way to weight the ABC draws using this exponential kernel that requires no ad hoc scaling or ad hoc thresholding. So imagine here, if we are not using the K hat, we're using the true empirical KL, like the term over here. Then essentially, immediately we are recovering the true posterior, but because of the difference between the KL, the K hat and the empirical KL, now we rewrite the approximated posterior as the true posterior times this exponential tilt function. And another way of viewing this approximated posterior is that we can view the product of the true joint likelihood and the exponential tilt function as the likelihood, as the true likelihood under a misspecified model. So
sorry.
using this.
Sorry, there is a question if that's fine for you.
Sure.
Hi, yeah, thank you. Yeah, just a quick question about the critic, the classifier. So to train a critic well, you need to be able to generate data, simulated data that approximates the real data well.
Yeah.
Otherwise, you're going to get a poorly performing critic. So the question is, how are you doing that before you actually have a good estimate for the parameters?
So are you? I'm not sure if I follow exactly. So are you suggesting, how do we probably how we determine are we choosing the correct, like the proper classifier?
Yes.
Or if the classifier is learned well enough?
Yeah, exactly. So how are you training the classifier?
So for here, I guess if for real data analysis, we always start with simulated data set. So usually we make sure the sample size, in the simulated case, the data set is the same size as the real data set. And we're trying to test do this calibration of the classifier and the simulated data sets.
So the parameters you're using for the simulations that you train the classifier on are chosen how? So the situation where you're actually trying to fit a model, so you don't know the correct parameters. How are we going to generate simulated data to train the classifier? Because we're
I'm still not sure.
So if the data you use to train the classifier is poor, in the sense that your simulated data is not very much like the real data, then you'll get a poor classifier. So so one of the reasons why GANs work well is that you're simultaneously improving your ability to synthesize the data at the same time you're training the critic.
Yeah,
So
so
if you don't actually have a well-fitted model, I'm just how are you going to be producing good simulated data for training the critic?
So for the first paper here, so first we're focusing on the situations where the model is correctly specified. So we assume this the p theta is like the true data generative process. So basically, if you imagine this is the GAN case, the generator is known in this case.
Okay, so you can generate simulated data from the correct model in that case.
Yes.
Yeah. Okay.
Yeah.
So.
Yeah, but our second paper is actually using even more. Our second paper is using the GAN ideas even closer to the original GAN paper, but we still assume the true data generating process known.
Okay, great. Thank you.
So now I will continue. So let's go back to this exponentially weighted kernel. As I just mentioned, we can always view this as the likelihood under a misspecified model. So then we can use the classical Bayesian consistent theory to show that that leads us to concentration. The concentration of this approximated posterior will be around this theta star, which is the KL projection point of the true model onto this misspecified model space. And so although this theta star may not be the most natural centering point that we want, there's a bias between theta star and the theta null that we want. But in our simulations and also the empirical analysis in the paper, we observed that usually this bias is not too concerning when the when this machine learning classifier is expressive enough. And now I wanted to take a closer look at this Lotka-Volterra model again. I wanted to show why this is like a perfect example to illustrate the power of ABC methods. So here we fix the value of, so this model is prescribed by 4 parameters. And here we fix the value of θ2 and θ3 at its true values. And we basically do a uniform scan across the prior area of θ1 times θ4. And on the left plot here, we observe that the true value lies in this lower left corner of the entire prior range. And for most area of this prior, the estimated likelihood is very flat. So imagine if we start a MCMC chain randomly somewhere in this flat area, it's gonna take forever for the MCMC chain to find this promising neighborhood around the truth. And that's where the independent sampling of the ABC strategy may have an advantage over the MCMC method. We also include a comparison of our ABC methods with other commonly used ABC methods that use energy statistics, maximum discrepancies, the Wasserstein distance, and also another classification-based method by Guffman and his co-authors using the classification accuracy as the data discrepancy metrics. So for our methods, we use a random forest classifier here. So all the histograms here are the posterior returned by the accept-reject ABC. We use this blue solid curve to represent the posterior that is returned from the exponentially weighted kernel. And I wanted to draw everyone's attention to this parameter θ3, which we feel this is which seems to be the most difficult to estimate among the 4 parameters. So most of the other methods return a very flat posterior, but still our method using this exponential weighted kernel is able to identify the correct location of θ3 while still providing a very tight credible interval. Here are the conclusions for the first paper. So here we develop an ABC approach that obviates the need for summary statistics. And we consider 2 versions of weighting the ABC draws. The first one is still accept-reject ABC. And the second one, we propose an exponentially weighted ABC that requires no ad hoc thresholding or scaling and is directly motivated by the connection between KL divergence and the likelihood ratio. Yet there are some limitations to this method. The first one is when we don't have independent copies of the data set, it is unclear to us how to construct a reasonable classifier for dependent data sets. And the second one is for this method, we need to train a new classifier for each ABC draw. So the computation costs can be a little bit heavy. So these are also like 2 things that motivate us to start working on our second paper, which relieve the limitations here, but still using the same adversarial learning ideas. So the paper is Adversarial Bayesian simulation. And this paper is more directly related to generative adversarial networks. So for people that are familiar with GANs, you probably already noticed there's some similarity of the first method to the GANs. So for the first paper, we are more exploiting the power of discriminator. The generator is known. That is the true data generation process. So this paper will be more following the will be more aligned with the GAN literature. So let's start with the basic GANs for people may have seen these pictures many times, but I download like a new 6 fake human images from this website. This person does not exist. I wanted to show like nowadays with the iteration of the different variants of GANs, the power of the generator can achieve like such high resolution of the human face images. So the idea of the traditional GAN is like an interplay between the 2 players in the games, like generator and the discriminator. So the generator will act like a counterfeiter, and the discriminator is acting like a cop trying to catch this counterfeiter. But it's a little bit more than that, because the generator will receive feedback from the discriminator so that it can improve itself. So like as this like toy example here, the goal of the generator is to create produce fake dollar bills that is look similar to the real distribution of the dollar bills. So the generator may start at just a random blue rectangle with some scribbles on it, and it passes it to the discriminator, and the discriminator will immediately distinguish the fake dollar bill from the real dollar bill. And then the generator will receive the feedback from the discriminator. Oh, you are doing a really bad job, but here are the things you can improve yourself. So the generator learns, oh, maybe I need a human head in the center of the dollar bill, and I may need like a number on the upper left corner of the dollar bill. So this is like the second fake dollar bill that it generates, and it returns to the new one to the discriminator again. But still, it's an easy task for the discriminator to tell them apart. So discriminator will provide some feedback to the generator again for it to improve itself. So step by step, the generator learns how to produce a fake dollar bill that looks indistinguishable to the real one. The training process will stop until the fake one and the real ones are indistinguishable for the discriminator. So to put down in a mathematical formulas, this is essentially a 2-player min-max game where the generator trying to minimize this binary cross entropy loss between the real and fake, and the discriminator trying to maximize the binary cross entropy loss. So here, the case is the generator learns to approximate the marginal distribution of X. So for marginal, because the traditional GANs can only handle the unlabeled data sets. So I would just use marginal distribution of X to refer to that. And basically, we always simulate latent variables from this noisy distribution, usually a standard Gaussian. We pass it through the generator, so it can generate a new copy of the like a fake image or the fake dollar bill. And the goal of the generator is just to learn a push forward mapping that moves the distribution of the latent variable pi z to the distribution of pi x. So what if we wanted to generate like fake images conditioned on some extra information? So now we want more than just like a fake human. We may want to generate a fake female face or a fake male face. Or in the animal case, we can generate a fake cat or fake dog. So the structure of the neural networks are similar to before, except that now we have label information entering both the generator and the discriminator. And this is what we call a conditional GANs. So now the goal of the generator becomes we wanted to generate a fake cat, or we wanted to generate a fake dog. So it's generating fake images given the labels. And the task for the discriminator becomes is trying to distinguish the pairs of the image and the labels. So you will try to learn how is the real cat different from the fake cat? How is the real dog compared to the fake dog? So it's now more like apple to apple compared to orange comparison. And since the conditional GAN can generate a fake image given the labels, we can also map it to why not we use the same idea to generate fake parameters given data set. So now this time we feed the pairs of parameters and the simulated data set to the conditional GANs. And the goal of the generator becomes we wanted to generate fake parameters given the data set it received, with the latent variable zi. And the task for the discriminator becomes how to distinguish the pairs of the true parameter and the data, the joint distribution of the true parameter and the data set, and the joint distribution of the fake parameter and the data set. Again, to put it down in a mathematical formula, now we still have this two-player min-max game formulation, except that this time we have this condition the data set entering both the discriminator and the generator. And while the discriminator is trying to tell the difference between the joint distribution of the joint distribution of real data set and the real parameter and the data set, and the joint distribution of the fake parameter and the data set, while we fix the marginal distribution of the two parts the same. So the marginal distribution of the two the real and the fake part are the same. Essentially, the discriminator is also matching the conditional distribution of the parameter given the data set too. And when both the class of generator and the discriminator class are flexible enough, the oracle solution to this minimax game can be written in the following form. So basically, the generator will return us the conditional distribution of parameter given the data set it received. And we wanted to highlight that during the training process, the observed data set is not used. So we only used a simulated pairs of theta and synthetic data sets. So this so the oracle generator is supposed to give us conditional distribution for any data set in this in the marginal distribution of X. And the discriminator, the oracle discriminator, will return us the ratio of the two joint distribution, the joint distribution of the real parameter and the data set, and the joint distribution of the fake data set, fake parameter and the data set. So this is something we have already seen in the previous classification trick slide. So essentially, the generator with this condition is learning a push forward mapping from the latent variable distribution to this conditional distribution. And we wanted to highlight that again, the observed data set is not used in the training process. So the generator is trying to learn from the simulated pairs a general push forward mapping. So it might be not that straightforward. So we wanted to use the simpler Gaussian example again. So imagine we are trying to estimate the location parameter from a Gaussian for a Gaussian distribution. We assume a standard normal distribution for the location parameter. Then we can generate simulated pairs of this theta and the xn. And essentially, this push forward mapping can be written as a linear combination of this latent variable and the data set that we received. So this linear transformation is sometimes people refer this to as a reparameterization trick, but this is a simple case. In real application, the G function can be more complicated than just linear transformation. And once we obtain this general mapping, we plug in the observed data set and we filter the latent variables through this generator. We obtained approximated posterior draw that is conditioned on the observed data set. So despite the attractive property of conditional GANs in real implementations, it suffers a lot of the training issues. And one of the most commonly seen issue is that the gradient of the generator may vanish when the discriminator is too strong because of the log loss formulation in the binary cross entropy loss. So people have proposed another variant that use the Wasserstein loss. Basically, we replace the we replace the log of the discriminator with this critique function that belongs to this class F that are one Lipschitz with respect to the parameter. So here is an algorithmic description of our method, the Bayesian GAN sampler. We parameterize both the generator and the critique function with a neural network. And the first step, we still generate this ABC reference table, basically simulated pairs from the joint distribution. And we feed the pairs into the Bayesian GANs that is trained using this empirical version of the Wasserstein loss. And once we obtain this generator, we plug in the observed data set. We filtered the random latent variables, and we obtain posterior draws from the generator. And in our paper, we provide convergence results for this approximated posterior in terms of total variation distance. So we first introduced this prior concentration in a condition that is commonly seen in a lot of the Bayesian literature. Basically, we need to ensure we have enough mass around the truth so the data can provide us enough evidence to find the correct location. And the convergence here depends on three terms. So the first term is the ability of the critique function to express the class of density ratios. The second term is the ability of the generator to approximate the average of the true posterior. And the third term is a condition on the number of pairs of simulated parameter and the data set. It depends on the complexity of the critique class and this class H, which is the composition of critique and discriminator function, and defined in pseudo dimension. So basically, these theoretical results provide us some guidance on what is the appropriate architecture that we need to consider for the generator, the discriminator, and also the sample size, like the number of simulated pairs of parameter and data set that we may need to achieve desired convergence. Here's a toy example, like we assume we observe 4 pairs of bivariate Gaussian. We make it artificially a little bit difficult by introducing the square term of θ3 and θ4 in the covariance matrix. So now we will expect the bimodal shape in the posterior of both θ3 and θ4. And in this case, the true posterior is computable. So we include this purple dashed line as that is the true posterior in the comparison. We compare our method, the Bayesian GAN, with ABC method using summary statistics, Wasserstein distance, and another simulation-based inference method, the sequential neural likelihood method. So from the posterior plots here, we observe that the posterior return from our Bayesian GAN sampler is the closest to the true posterior, and we wanted to also draw everyone's attention to θ3. So in this case, we observe that the ABC methods using summary statistics and the Wasserstein distance may not perform that well in identifying the bimodal shape of θ3. And as I mentioned before, during the training process, the observed data set is not used. So that leads the performance of this Bayesian GAN sampler to be somewhat uniformly over the entire domain of the marginal distribution of the data set. But we only care about the performance that is conditional on the observed data sets. So we consider 2 types of approaches to enhance the local performance. So the first one, we consider incorporate the observed data set in the proposal distribution. And this is leads us to consider this 2-step refinement. And for the second approach, it is inspired by adversarial variational based method. we are able to incorporate the observed data set in the training process. For the two-step refinement, this is somewhat not new in the ABC literature. So basically, for the first step, we still generate the ABC reference table from the prior. We pass it to the Bayesian GAN sampler. We recover the posterior from the Bayesian GANs. So the Bayesian GAN, so the first step posterior may tell us, oh, the true may lie in this lower left corner. This is the promising area that we need to zoom into. So the idea here is, even though the posterior return from the Bayesian GAN may not be precise enough, but it provides us more information and a higher mass around the truth. So we can use this as the prior for the second step. And we generate a new ABC reference table from this posterior. We pass it through the Bayesian GAN again. And for the second step, the Bayesian GAN should be able to further zoom in the neighborhood around the truth. But as we are Bayesian, we care about we are not using the correct prior in the second step. So for the second step, we need to adjust the fact that we are using the wrong prior by introducing these importance weights. Basically, it's the ratio of the two priors. So now the approximated posterior samples will be pairs of the simulated parameters and the importance weights. The second approach is inspired, as we mentioned, is inspired by variational Bayes. So variational Bayes has been often used to obtain finer and tighter posterior approximation. So here we replace this two-player min-max game with basically a max-max game. Here we are trying to find the generator class that maximize this evidence lower bound. Because of the evidence lower bound is like the KL divergence between the approximation class and the true posterior. And we can use the classification trick again. So here, the part in the red box, the expectation, the empirical version of the expectation is just simply simulations from the generator with the observed data set plugged in. And for the log density ratio part, although it's implicit, we can always use the classification trick to replace it with the logit transformation of this oracle discriminator. And since we do not have this oracle discriminator, we replace it with a trained discriminator that is trained on the pairs of the joint distribution of the true parameter and the data set and the fake parameter on the data set. So the difference of this variational Bayes and the previous vanilla GANs is that now the discriminator learns globally, which is trying to distinguish the pairs of the joint distributions, but the generator learns locally. It's only focusing on it's only updated on the observed data set. So let's review this toy example again. So we wanted to highlight that with the local enhancement approaches, both the two-step refinement and the variational Bayes version are able to further reduce the estimation bias and provide tighter credible interval compared to the vanilla GAN version. We also report the maximum discrepancy between the approximated posterior and the true posterior. So with the two-step refinement, we observed that the distance between the posteriors got further reduced. So that means the two-step refinement not only reduced the estimation bias, but also further the distribution, reduce the distance between the distributions. And let's revisit the Lotka-Volterra model one last time. So we still use the same setup as before, except that now the observed data set is a one single time series. So basically the observed data set is a 1 times 400 vector. But even with this one single time series, our method using the two-step refinement is able to identify the correct location of all the parameters while providing very tight, credible intervals. And it also get rid of the limitation of our previous ABC papers that we need the ID copies of the time series. Here are the conclusions for our second paper. So in the second paper, we propose a Bayesian GAN sampler that extend the limitation of our previous papers. So first, it can be applied to dependent data sets with maybe only one observations. And the computation called the neural network. We provide convergence results in terms of total variation distance. And we also consider two types of local performance enhancement in the paper. Well, the first one is we use the observed data set in the proposal distribution to conduct a sequential refinement of the posterior. And the second one is inspired by adversarial variational base. We incorporate the observed data set in the training process. So that concludes my talk today. I'm now ready to take more questions.